So let's start with our intro to nonlinear models. One thing I wanted to talk about first is that the typical architecture of neural networks, they are generally called feed-forward, as shown here. Feed-forward just means that the data flows in one single direction from the input layer, from the input data, through the hidden layers, and then through the output layer, and finally to your output results. So it's unidirectional, and this type of architecture that has successively connected layers sequentially like that, that's why we use the TensorFlow sequential function to create a model, is called feed-forward neural network. So if you see that name when you browse through the literature, this is the most typical type of neural network that people implement to solve several types of different problems in several fields with different complexities. In the previous practice session, what we did was to just create a linear neural network. We didn't have many layers like this. We just had one single neuron that was connecting the input data to the output data. So unfortunately, this model is too simple. If we have complex nonlinear data, we would not be able to fit the target function. We would not be able to fit the model to the data if it was more complex. In more official terms, we can say that this model is too simple to fit the universal approximation criteria that I talked about before. And if we have a model with two layers, we would have, for example, one neuron here, one neuron here, or two layers of multiple neurons, we still don't have any hidden layer between those inputs and outputs, and we still don't have any nonlinear activations. So although we are increasing the complexity a little bit versus this previous model here, we still don't have what we need to follow the universal approximation criteria. So for solving that problem, usually what we do is to have a neural network of at least 3 layers total. One is like the input layer of neurons. The other one in the middle is the first hidden layer and an output layer. And on top of the input layer and the hidden layer, we have nonlinear activations. So now we are fulfilling the 2 criteria. We have at least a minimum set of complexity and a minimum amount of nonlinearity in this model. Given that we have a sufficiently complex neural network with nonlinear activations, we would theoretically be able to map any sort of target function, no matter how complex and how nonlinear your data is. Let's start today. We're going to go first and build our nonlinear data. We're going to use the same package that we were using before, the scikit-learn, and we're going to use this sub module here, the sub package datasets to use the make regression function to create our synthetic or simulated data set. So you're going to set a total of 100 samples, just one feature. Let's keep it still a bit simple and easy to run. We're going to set a bias of 0 and noise of 10 to increase the complexity a little bit. And we're going to fix the random seed to a fixed number so we can make this random data set reproducible. So this is very similar to what we did before. The difference here is that after we create our linear data set, we convert it into a nonlinear distribution by adding a polynomial factor here. We're going to also decrease the range of the data a little bit to make it more simple to fit. And we're going to shift the intercept of the data a little bit as well. We're going to shift it to the left a little bit. So after we do this conversion to polynomial, we're just going to plot to see how the data looks like. So before we had a pretty much linear data where the data points had a little bit of noise, but they all follow a simple linear equation. So let's see how it's going to look like now. It's running, shouldn't take that long. And we got a polynomial type of data structure here. So now that we have our known linear data, let's see what happens if we take that same model that we built before, that linear model, a linear neural network with no nonlinear activation and just one single neuron, and let's see how well it does. So for doing that, just a recap from the previous session, we're gonna import the TensorFlow package that we use to implement our models. We're gonna create an empty model first, and then we're gonna populate this model with just one single layer. We're gonna use the add function to add a layer, and we're gonna define the layer with this function here, TensorFlow tf char as layer stance. And this function takes as argument the number of neurons that we want and the input shape that is critical to make this neural network support the input data format that we have. Since we have one feature only, it's just one vector of values, we set an input shape of 1. So we're going to compile that model by adding an optimizer that will fit our model, that will do all these optimization steps for us, so we don't have to fit anything manually. And we're going to set the loss function as mean square error, the same function that we used before, compare our ground truth data to the predicted values of the model and quantify how wrong our model is. So as lower this number of mean square error, better our model is. I'm going to use model summary to show how our model structure looks like, how many parameters it has, and we're going to split our data into batches. As I talked before, splitting the data into batches helps us to get more parameter updates, more weight updates in our model, and having more updates, it may help us to find the best parameters as possible. And we're going to use the model fit function to finally train our model for 100 epochs. So it means that we're going to pass through all the batches, updating the model weights 100 times. And we're going to specify our input data as we define here by our X and Y that we simulated. And finally, we're going to extract the predicted values from our model so we can plot those predicted values versus the ground truth values that we generated from the simulation. So let's see how this linear model is going to do. It shows here that our model, let me go up first, shows that our model has 2 parameters here, 2 trainable parameters, or weight and bias in the linear equation. And as you can see, the loss value pretty much stick to 0.03. And we basically have a linear model trying to fit to a nonlinear training data set. Although the loss doesn't look that bad, we can see that from the data points here in orange, that is our predictions, versus the blue data points here that are the original data, that our linear model is not able to fit properly to this nonlinear data. So how can we solve that problem? We first can try, for example, to add more complexity to our data. We can add an extra neuron. But as I mentioned before in the theoretical session, what really gives nonlinearity to the data is the nonlinear activation. So I'll just demonstrate here that if we just try to add another neuron, we're just gonna, another layer, we're just gonna increase the complexity of the model a little bit, but we may not be able to model the nonlinearity of the data still. So I'll just show how the model looks like with 2 layers. So before we had only dense 1 with 2 parameters. Now you can see another layer here, the dense 2 with another 2 parameters. So we have a total of 4 trainable parameters. We have the weight and bias of layer 1 and the weight and bias of layer 2. So that's why we have 4 trainable parameters. We can try to go ahead and fit that model. So we are getting the same loss value and the same fit. So just adding more linear neurons doesn't help us to get the model to fit to nonlinear data. The same result as before. Now let's try to add finally a nonlinear activation. To convert our neuron into a nonlinear neuron, we have to add an input options into our layer dense function. We specify the number of units the same way that we did before. We specify the input shape the same way that we did before, but we're gonna set an activation equal. Then we can pull the activations from the keras, the TensorFlow keras package, and we can specify what type of activation we want. These activations here class has many nonlinear activations available. It has sigmoid, 10H, ReLU, all those activations that I was talking about in a few sessions ago, but we're going to stick here just for demonstration. We're going to use the ReLU, that is one of the most common activations for deep artificial neural networks. Here we have a first layer with one single neuron as we had before, but now we are adding a nonlinear activation. And then next, we add the new layer. We still add the second layer as we did before, but let's just keep it like that for now to see if just adding one nonlinear activation, we are able to model or not this nonlinear data. And as you see here, I'm not putting an argument of input shape here. I could do that and manually specify what is the input shape of my previous layer. So the input of this layer is the output of the previous layer. But it's going to be complicated when we start to increase the number of neurons per layer and the number of layers. So if you don't put anything in the input shape, TensorFlow will detect automatically what is the shape of the previous layer. So you won't have to worry about shape mismatches. So this is going to be our output layer, and this is going to be our first layer of neurons with a non-linear activation. So let's see if adding that is going to help. So we already built our model, same number of parameters as before. We are only adding an activation that is nonlinear. Let's see. And the loss decreased a little bit if you compare to the previous value before. So we got a little better. We got a little bit nonlinear here. It's making a little bend here, a little curve, but we quite don't have the complexity that we need yet to fit to this whole shape here, to this whole distribution of the data. So what we can do in those cases is, for example, increase the complexity in the number of layers or increase the complexity in the number of neurons. So let's see what happens if we add an additional layer. So we have, for example, one first layer here that processes the inputs that has a nonlinear activation. We have a hidden layer in the middle with a nonlinear activation as well. And then we have our output layer that is usually linear to represent our linear output. So that is more similar to the neural network that follows the universal function approximation, except for the complexity. So we have only one single neuron per layer, so we may not have complexity enough. We have nonlinearity, but we are missing some complexity. So we built here a model. You can see 3 layers. Each of the layers have one weight and one bias to be trained, to be fit. So a total of 6 trainable parameters. So let's try to fit that model and see how our data looks like. Should be quick. Let's see. Make it down. Yeah, we are getting a little better, a loss of 0.01. So it's helping, but we are not quite there yet. We're not fitting that perfectly to our data. We are adding some nonlinearity, but looks like we are missing some sort of complexity. So what happens if instead of just adding new layers that are too simple, that have just one single neuron, we take our hidden layer from the middle here and we add 10 neurons to that layer instead of 1. Let's see how that would help. I'm putting all the code here directly. We are repeating the compiling, summary, fit, etc. So it's just simpler if we just plot everything. Looks like we are creating a little valley here. Kind of wants to get to the shape, but we are not quite there yet. So we only increase the complexity of one layer a little bit. Let's see what happens if we add 1,000 neurons. Let's take a look. It's gonna take a little bit longer to train, but we are dealing with small neural networks, so it should be fast. It's still not working that great. So sometimes taking just one layer and adding a lot of complexity, but then keeping the other layers too simple doesn't help us to make a smooth transition between fitting to a simple linear data set to a more complex nonlinear data set. Usually it's recommended to have a more gradual transition in complexity rather than having a layer that is too simple, another layer here in the end that is too simple, and then a very complex layer in the middle. That doesn't help that much. So we have a bunch of parameters, have thousands of parameters, but our model is still not great because we are not implementing it in a very smart way. We tried to increase the number of layers, fixing the number of neurons. So we tried to increase the depth, but keeping the width of one. That didn't work that well, helped a little bit, but didn't solve the problem perfectly. We also tried to increase the number of neurons a lot of just one layer, of just a hidden layer, increase the width of our neural network alone without increasing the depth too much. And that didn't help so much. Let's see, what if we increase to 100 layers? So I don't want to do that manually. So what I'm going to do here is to create a for loop that for every number in a range of 100, I'm going to repeat this task here of adding a layer. First, I add my input layer here with one neuron with a nonlinear activation. And then I add another 100 hidden layers here, also with nonlinear activations. And then I add my output layer here that is linear to represent our linear outputs. So if you have a situation where you have to build a very deep neural network with, let's say, 5 or more hidden layers, you can basically use a for loop like that to keep adding more and more layers automatically. So you don't have to copy and paste a lot of code. So this is a more elegant solution when you have very deep neural networks that need to be implemented for very complex data. So we could do that, and we would have many layers with just 2 parameters. So we could increase the number of parameters by just increasing the number of layers like that. So we have 204 parameters. We can try to fit our model. Let's see how the results are gonna look like. Well, I have a little spoiler there. What, I think I shifted. So it didn't help at all. Let me see if I'm in the right place. Yeah, so basically that didn't help at all. So adding too many layers that are too simple is not helpful. And adding just a single layer that is too wide also doesn't help. So the best recommended practice is to actually gradually increase both the things at the same time. You increase both the number of neurons to have at least 3 layers in your model to fit the universal approximation. And you increase also the number of neurons in both of those input and hidden layers. We cannot increase the number of neurons in the output layer because the output layer should have the same shape as our output data, which is we have just one feature. So it makes sense to have one neuron. So let's try to do that. Let's get back to our original form. 3 simple layers, 1 input, 1 hidden, and 1 output. And just let's increase the number of neurons to 8 in both input and hidden layers. Let's see what happens. So we're gonna see we have less parameters than we had before in that big model that we built. And let's train our model. Let's see how it works. A little longer. And it's much better than before. It's following that polynomial shape that we really wanted to follow. It has a little kink here, but this is already much better than what we had before. So that is the type of increasing complexity and nonlinearity that is most successful when you are trying to implement a model that wants to represent nonlinear and complex data. And we see here that the loss is very small. 0.001, much better than what we saw before for those other attempts that we did. So this is how I would troubleshoot a model. When I apply a model in a new data set that is complex and nonlinear, I gradually increase the number of layers and at the same time the number of neurons. And then I see how the results look like, how it fits to the data. Let's see if we keep gradually increasing the complexity by adding an extra layer. So now instead of 3 layers, we're gonna have 4 layers. And instead of 8 neurons per layer, we're gonna have 16 neurons per layer. So again, we're gonna have a depth of 4 layers, and a width of 16. So the maximum number of neurons per layer is 16. We're gonna simulate the same data as we did before. I put everything here just in one code block to make things easier to run. So let's see how the results are gonna look like. I'm also training for a few more epochs because as the complexity of your model increases, it's very common to see that your model needs more epochs to fit all the parameters. So if you have a lot more parameters in your model, it's a good strategy to increase the number of epochs. So you allow the model to do more weights updates and compute the gradients for longer, for more often, so it can have more chances of finding the optimal weights for this model that has many weights. So you have more parameters, so you take longer to fit those parameters. And finally, we have a loss of 9 to the minus 4. So we got basically a perfect fit to this nonlinear polynomial data set. And yeah, it definitely worked to increase both depth and the width of the neural network at the same time. And of course, the nonlinear activations were essential. Otherwise, we would just have a very complex linear model here. So this was a demonstration of how we can, at the same time, implement nonlinear neural networks and experiment, do some tweaking in the complexity of the neural network so it can start to fit to any type of problem, to any type of data complexity and nonlinearity.